Hello, Health Science 4502 students. I hope you're doing great. Hopefully, everything's going well with your papers and your presentations. Now, a lot of questions in regard to submission for your paper and your presentations. You're going to send those to me over email to william.vandyke@csusb.edu. A lot of people use like Google Drive for your paper and your presentation because they're too big to email. So feel free to do so. Whatever's easiest for you to get those to me, please do so. This is again, I want to try to get through this lecture and not make it too painful for you because I want you to be able to focus on your paper and your presentation. So you'll see that I'm going to kind of skip over some of the materials that aren't quite. They're really not something that we do so much in the field. But certainly they're here for you to learn. If you have questions about them, let me know, and I'm always happy to have conversations about these things, as you know. So we're gonna move through this material. For the course tonight, we're talking about gases and vapors, and I'm assuming that everybody's taking chemistry, so I'm not gonna, I'm not gonna sweat you on the math on this. I've given you some math questions in the past, and I appreciate all the hard work that you've done on those, and I think you all know how to make calculations for gases and vapors by this point. So they're here for you to review, but certainly not something that you're going to need to do for your upcoming tests. Okay. So let's move through the material. Slide 2 is the title slide. Slide 3 is the section A that we're moving into. So slide 4 is where we start to discuss the definition of gas. So gas is essentially a normal, formless state of matter that at room temperature and pressure has a low density and viscosity, readily and uniformly distributes itself throughout any container, right? So if you have a box, it fills up the box. If you have the room, it's going to fill up the room uniformly, okay? Gases and vapors can be organic or inorganic in nature. There are some examples there like oxygen, which exists as O2, sulfur dioxide, O3, which is, as you remember, is ozone, nitrogen dioxide, formaldehyde, and methane as well. So with vapors, we're dealing with a gaseous form of a substance which coexists as a solid or liquid at normal temperature and pressure. So vapor is going to be a little bit different in regard to that gaseous form of a substance that coexists as a solid or liquid. So the vapor is coming off of the gas. So right, we have a thing of gasoline. It's existing as a liquid, and it's pumping off gasoline vapors. Okay, so that's a coexistence process. So we can think about mercury, H2O like water can make water vapor, benzene, acetone, ethanol, things like that. On to slide 6. So we're all familiar with STP, of course, not the band that unfortunately we lost the lead singer to a few years ago. We're talking about standard temperature and pressure, and I think you're all familiar with these, right? At 0 degrees centigrade, 760 millimeters mercury, 32 degrees Fahrenheit, 29.9. 1 mole of any gas occupies 22.4 liters at standard temperature and pressure. Again, I'm going to kind of jump through this stuff pretty fast. I assume that you all know this. So that's STP, and then we have normal temperature and pressure. You can read that as well. On to slide 7, discussing vapor pressure. Vapor pressure becomes important because, from an occupational setting, if you have high vapor pressure, you can start running into danger. But certainly, low vapor pressure can be an issue with specific things as well. So this is the pressure exerted when a solid or liquid is at equilibrium with its own vapor. The higher the vapor pressure, the more volatile, as I had mentioned before. So with the chemical, that's measured in mmHg. It's temperature dependent, as you remember, and the higher the temperature, the higher the vapor pressure and equilibrium and concentration. So slide 8 has a U-tube manometer connected to a flask, and you can essentially see this vapor pressure process. When you add heat, it's going to make some changes to it. Slide 9, given two substances of the same volume, which one has more potential hazard? So if you have motor oil and ether, this is just kind of a general question. Ether has more potential hazard than motor oil because it's high vapor pressure and volatility, right? So we're all familiar with this. Again, I want to run through this stuff fairly quickly because I want to give you a lot of time to work on your paper and your presentation. Some health effects. So gases and vapors are are governed in large part by diffusion, right? So they're gonna move to fill those spaces. They're gonna diffuse into those open spaces. Exposure can be caused through absorption in the respiratory system, largely dependent on the gas, right, and the solubility in the mucous membrane. So some of these things are very readily absorbed into the respiratory system and can cause extraordinary damage. They can cause local irritation. Systemic toxins distribute in solution through the blood and the lymphatic system, so they can be very, very dangerous. Moving on to slide 11, these are some examples of the health effects, and this is probably where I might draw some test questions from. So an asphyxiant is going to cause you to become unconscious. It'll knock you out. So asphyxiants can also lead to death, right? So what happens if you're exposed to too much carbon dioxide? Eventually, or carbon monoxide as well. Carbon monoxide is very dangerous. Carbon monoxide is going to cause asphyxiation. It's going to cause you to fall asleep and pass out, and then it's going to kill you. So it is very, very dangerous. And then we have irritants, like, and certainly these can be fatal as well. An irritant is going to cause inflammation, most specifically in the lungs and the respiratory tract, from things like chlorine or formaldehyde. So y'all remember Lumber Liquidators was selling materials that had formaldehyde, and they had a massive lawsuit where they had to pay to have all those materials removed and replaced. But chlorine can cause real irritation in the respiratory tract. Then we have anesthetics, which are going to cause an insensitivity to pain. So yeah, these are good things. We definitely want anesthetics, but they can be dangerous as well. So too much exposure to toluene and benzene can be anesthetic in nature. So if you're writing a paper on any of these, you can include some of this information in your paper, but make sure that you know what you're talking about and cite reputable sources. Not me. I'm not so reputable. And I personally would not use my PowerPoint slides as a quotation, a source of information. But certainly this specific slide, these come from Johns Hopkins, so you can actually use them. So on to hepatotoxins. So hepatotoxins are going to cause damage to the liver. They can be very, very dangerous. And then we have nephrotoxins, which are going to cause kidney damage. And certainly toluene and xylene here again. Neurotoxins are going to cause damage to the nervous system. Hematopoietic toxins like benzene and carbon monoxide. So hematopoietic toxins will cause damage to the hematopoietic tissues in the body, and this can have an effect in regard to the lymphatic system, and it can also have an effect on the parts of the body that generate bone marrow. So that can be very dangerous because, as you know, bone marrow is very important to creating things like red blood cells as well. Then you have pulmonary toxins, which will have an effect on the respiratory tract, certainly the lungs, and it can damage the lungs. So with pulmonary toxins like nitrogen dioxide, phosgene, things like that can be very dangerous for your lungs. And then we're all familiar with carcinogens like benzene, vinyl chloride monomers, and things like that can be very, very dangerous in regard to their effect. So section B is the gas laws. I just want you to kind of remember these. I'm not going to test you on them, but I want you to, I'm assuming everybody took chemistry, so you should be familiar with Boyle's law. P1 V1 equals P2 V2. So V1 over V2 is equal to P2 over P1. So keep that in mind. Boyle's law is pretty straightforward. There's some examples there if you want to try to work through them just to see if you remember how to do them. And then you have Charles' law. At constant pressure, the volume of a gas is going to be directly proportional to its absolute temperature in kelvins. So again, I'm not testing you on these things, but you can take a look at them and just run through the calculations and see if you still know how to do these, and you're going to end up with answers that are listed here. So you have the answer right in front of you. And then on to slide 18, you can actually combine Boyle's and Charles' law to get some very dense equations. And on slide 19, you can see those equations. On slide 20, you can see an example of that with that combination. And then you have slide 21, which I sincerely hope you all remember this. Now, while we don't use it a lot while we're working out in the field, you really should know the ideal gas law, which is PV equals nRT. Pressure times volume is going to be equal to the number of moles of gas times the molar gas constant, which is 0.0821. and temperature times temperature. So you really should know PV equals nRT. And again, I don't expect you to remember the molar gas constant, but you should probably at least remember the ideal gas law formula, PV equals nRT. Okay? Not that I'm going to test you on it. And then there's an example on slide 22. And then slide 23 is going to be concentration units. So this is kind of cool stuff. Gas and vapor concentrations. You're going to have a concentration which is equal to mass of the contaminant over the volume of the air, equal to the volume of the contaminant over the volume of air times 10 to the sixth. Okay, so concentrations are going to be in milligrams per meter cubed or parts per million. So you can see on slide 25, there's just a little bit more information on this. And again, I promise you, I'm not going to test you on this stuff. I really want to move through this fairly quickly so that you can focus on your papers. And this is the area that I like to do it because, again, there's not a lot of this stuff that you're actually going to be doing. And if you do work fairly readily with this, you can certainly draw on your chemistry background to be able to extract these answers. So 26 is a conversion of units. Let's skip over that. It's pretty straightforward. If you want to figure it out, you can kind of run through some of these problems. If you can't get the right answer, let me know and I can help you with it. Slide 28 is a continuation of the conversion of units. And again, as I had mentioned before, not really something that you generally tend to do. On to slide 30, vapor pressure and concentration. And this is a calculation of a theoretical headspace with a saturation concentration. So again, this is a very worst case scenario. And this is going to be when you're looking at vapor pressure and concentration. It's going to be generated in parts per million, and it's going to be equal to the vapor pressure of a contaminant over 760. So you remember 760, an important number, right? And that's times 10 to the power of 6. So on slide 31, this is going to be vapor pressure and concentration, and this is going to be an example. Now, this is something that I actually do want you to work through just because it's fairly interesting. I'm not even going to put this on your lab. I just really want to let you have an example of being able to look at this because this is something that you'll eventually be able to use later on in one of the upcoming problems. So a large storage tank is partially filled with benzene and its vapor pressure is 82 mmHg at 20 degrees centigrade. What is the theoretical saturation concentration in the headspace above the liquid? So again, this is that saturation concentration at at 82 over 760 times 10 to the 6, and that's going to give you 108,000 parts per million. Now this comes in handy when like if you're looking at your concentrations in regard to specific materials. If you're looking at those things for your paper, it kind of gives you an idea of what's going on when you start to talk about parts per million. But again, it's not something that I'm going to test you on for the purposes of this class. Slide 32 is some general considerations. Okay, now this is what I kind of want you to focus on this part of the PowerPoint because it's got a benzene spill scenario that I really like, and this is the reason that I teach from this presentation is the benzene spill scenario is really good. So if you begin to work with hazmat after you leave Cal State San Bernardino, these are the kinds of things that being able to know how to do this is fun, but in general, it's really not something that you're going to put into practice in the field because you're really going to be able to go out with tools that are going to measure what your actual exposure to the spill is in regard to what your exposure is. So we're working with a scenario that you're working in a lab, and a 5 mil vial of benzene is spilled into a 400 meter cubed lab. If this was you, how would you react to that, and what essentially would you do? So what's reported to you, you're the industrial hygienist here, so this is a nice scenario for you. And how would you respond to that? You have a couple assumptions, okay? So the first assumption is that the room is sealed, all of the benzene evaporates, and the lab has well-mixed air. So it's sealed, it's not being pumped out, but it's going to be mixing with the natural air. So you're going to have a little bit of nitrogen, you're going to have some oxygen, you're going to have a little bit of carbon monoxide, carbon dioxide, but you're going to have these benzene vapors in the room as well. So with benzene, with the spill, so here are some terms that you're going to remember, right? You're going to start seeing things that are going to come up that you're going to know. The PEL, right? The permissible exposure limit for benzene is 1 part per million over an 8-hour time-weighted average. The density of benzene is 0.8 grams per mole. Molecular weight of benzene is 78 milligrams per molar mass. Since the concentration equals mass over volume of the air, we need to know what mass of benzene was spilled. So 5 milliliters, how much was spilled in order to compare it to the PEL. So we're going to be able to start taking these numbers and making some calculations to find out, is our exposure level too high? And as you remember before, we always err on the side of precaution, right? But is it safe for me to just go walking in there and doing my thing? So using the density of benzene, we can find the mass of the benzene that was spilled. So 5 milliliters times 0.8 grams per mole equals 4 grams of benzene that was actually spilled. Now we can calculate the concentration of benzene using the volume of air in the lab. So 4 grams of benzene over 400 meters cubed of air is going to equal 0.01 grams per meter cubed. Now we have to convert the concentration to parts per million, which you're familiar with. I hope you can do this. I'm sure you can. And we start by changing the units to milligrams per meters cubed, and that's going to equal 10 milligrams over meters cubed, right? So this is kind of an interesting process. And again, I'm not going to test you on this. This is all theoretical, and this is something that I want you to do it if it's fun for you. If you like numbers, kind of play with this a little bit. So as you can imagine, you spill some benzene, is it safe to walk in? Usually what you're going to do is you're going to walk in with a device that measures concentrations in the air, but you're going to protect yourself, right? You're going to use that scuba respirator just to make sure. You're always erring on the side of precaution. So now you're going to use, on to slide 37, now you're going to use the molecular weight, which is 78 milligrams for molar mass, and then we convert to parts per million through that long extrapolation process there, and you end up with 3.13 parts per million of benzene, right? So this is kind of the culmination of a lot of what we had looked at in the math numbers before, but again, this is so theoretical. I never do this stuff when I'm in the field, so I just kind of want you to get a look at this stuff. So with slide 38, we have 3.13 parts per million, which is 3 times the permissible exposure limit. But remember, you have to think about this. PEL is a standard designed to protect workers for an 8-hour day, so 5 days a week for many, many years. So when I'm looking at this, I'm going, yeah, I don't need to panic so much, but I still want to protect myself. So even though it's low at 3.13 parts per million, maybe I don't need to have a full face respirator on. Maybe I can just kind of go in there real fast and air out the room and everything's going to be okay. So some recommendations you could make as the industrial hygienist would be to close up the lab for a little while and open a window and turn on the ventilation process just to vent that stuff out of there and get it out of there. And certainly you're not going to run into any violations by opening up the windows and ventilating it through the HVAC system. But again, if it's recirculating into the rest of the space of the lab, it's not ideal, but again, it's not something that's going to kill you. So this is something that you can do. So the wrap up on this with regard to the benzene spill, the most important point that you're going to talk about in this is that you understand where the numbers come from and how they affect the situation at hand, standards and guidelines and purposes. So the most important thing for you as an industrial hygienist is to be able to explain the numbers, okay? Again, you're not going to explain them to me. You're not going to do this on a lab. You're not going to do anything of that nature. You're going to look at this. You're going to go, that's pretty cool. So now I can do a rough calculation if I want to figure out if I'm going to have a high exposure limit based on this spill. So I spill, 5 milliliters of benzene. Should I be concerned? Okay, and that's essentially what this teaches you through this process. And again, if we were in class together, we would do this, but ultimately, because we're trying to teach this over the computer, it's not really something that we can work through. And like I said before, I never do this stuff, and I've worked in a lab for years and years. So again, I want you to know how to do it. I want you to have a kind of rough idea of what I'm talking about here. So send me your questions if you have questions. And if you go into industrial hygiene, you want to be able to do this. You want to be able to help people out. You want to make sure that everybody is safe, and at the same time, you want to make sure that they are not stressing because of an exposure. On to slide 40. These are some general terms you may see with your chemical that you're discussing for your paper and your presentation. You may see UEL, which is an upper explosive limit. This is above which there is insufficient oxygen to cause an explosion. So if you pass the UEL, excuse me, if you pass the UEL, there isn't going to be enough oxygen to actually cause it to explode. But if you're below the UEL, then certainly that it can still explode. And then you have the LEL, which is a lower explosion limit, below which this amount there is insufficient fuel to cause an explosion. So with the lower explosion limit, there's not enough fuel. With the upper explosion limit, there's not enough oxygen. So if you're in between those 2 points, the lower and upper exposure limit, they can explode. Okay, if you're below it, there isn't enough fuel. If you're above it, there isn't enough oxygen. So you want to be aware of these things, because a lot of the time you're going to be working with chemicals, and certainly you want to know, is there enough of this material in this area that it could actually burst into flames and explode? And certainly this is a concern with things like nitroglycerin and things like that. But then you also have the flash point, which is the lowest temperature at which a liquid gives off essentially, it gives off enough vapor to form an ignitable mixture. And that can really be something to be focused on. So with flash point, you will probably see that with some of your chemicals that you're writing about. So this is essentially going to be that lowest temperature where you can have an ignitable mixture. So where can this burst into flames? So kind of keep that in mind. Have an understanding of these terms, but for the most part, I'm not going to make I'm not going to make this a part of your next test that comes up. So I just want you to understand these concepts. I want you to be familiar with them, and I want you to be able to have a rough idea of what they are in case it comes up in the future for you with your future career. So that's what I always like to do. I like to be able to review back on these things, but I can tell you that if you're going to become an REHS, if you're working with hazmat, you may from time to time kind of have to consider these things, like the flash point. Is there a flash point associated with this that can cause me problems? And you'll get a lot more information with on-the-job training. But again, I really want you to kind of have a rough idea of essentially what these things are. And flash point is kind of one of those things that will come up from time to time. It's something that you will have a discussion if you work with hazmat. So again, it's the lowest temperature. Oh, come on, stupid phone. So it's the lowest temperature at which a liquid gives off enough vapor to form an ignitable mixture. Okay, so you can imagine you're at this low temperature, like with gasoline. Gasoline doesn't have to be, it can be pretty cold, and it's still going to give off vapor. So from that liquid state, it's going to give off vapor that can, be ignited, that ignitable mixture. So gasoline, I off the top of my head, I don't remember the flash point of gasoline, but it's really, it's not that high. It's fairly low. So this is your video for week 7. I hope that this all makes sense. I know I moved through the materials fairly quickly, but I wanted to go through it fast because I really want you to be able to focus on your paper and your presentation. Start looking at those things. If you don't already have a chemical in mind, make sure that you get that process going. And actually, I think what I'm going to do is for the lab for week 7, I'm just going to ask you to tell me what your chemical is actually going to be. So that's going to force you to find your chemical. I want you to do that. So that's probably going to be, let's go ahead and make that your lab. I'm going to write it up and I'm going to post it as your lab, but your lab for week 7 is to basically just send me something that says the chemical that I'm writing on is XYZ, okay? It's benzene, or it's toluene, or I'm going to write about any other chemical. So find something that you like, write about it, and definitely enjoy that process. I encourage you to hopefully find a chemical that you either are currently working with or may potentially work with later on in your future career. You're all doing wonderful in this class. You're putting in a lot of hard work. I am grateful for all your hard work, and I look forward to a lot of very high scores in this class and some wonderful efforts in regard to the work that you've put in already. And I have every confidence that if I were to work with any of you in the future, that you would really do a wonderful job. I'm thankful for you, and I encourage you to continue working hard. Make sure that you have just some general knowledge of the concepts that I put forth. But again, there probably isn't going to be anything that you're going to be tested on in regard to vapors and gases. But make sure you understand upper explosive limits, lower explosive limits, and flash point as well. Okay, so with that, have a wonderful week, and definitely start looking at those papers and getting ready to kind of start working on those. Okay. So let me know your questions at william.vandyke@csusb.edu, and have a wonderful week.